Welcome to Lecture 11, 3.2, Measures of Dispersion. So the first objective is determine the range of a variable from raw data. Alright, so by definition, the range, with a capital R, of a variable is the difference between the largest and smallest data value. That is, R equals data value minus smallest data value. So for example 1, given the set of data to the right, compute the range. So what I'm going to do is I know that the range is largest minus smallest, so let's find the largest data value. The largest one I see is a 91, so we'll put that in there. And the smallest data value I see is a 62. So then let's go ahead and compute that. 91 minus 62 is 29. So the range is 29. Or you could leave it with R, 29. Now objective 2, let's determine the standard deviation of a variable from raw data. So one thing to note, as usual, is we're always talking about the population versus the sample. So the formulas change when you're looking at the population or if you're looking at the sample. First, we're looking at the population standard deviation, which is denoted with a sigma. And on page 127, if you want to look at that further. So there are two different ways we can write out the formula. There's the conceptual formula, which is going to be sigma, or your standard deviation. It's going to be equal to the square root of the difference between your first value and your mean squared. The second one, mean squared, plus so on till you hit your last observed value minus your mean squared all over n, where n is observations. And mean is the population mean. This all simplifies out to square root of the sum of the xi values minus mu squared all over n. So that's the conceptual formula. The computational formula, which is also equivalent to the one above, will be sigma, oops, that looked ugly, sigma equal the square root of the sum of the xi's squared minus the sum of the xi squared all over n divided by n. Okay, one thing to note. This one, you're adding up the values that you square. For the other one, you add up all the values and then you square the final product. So bear that in mind. Those are two different types of squares. Notes, there is a difference between finding the standard deviation of the population versus finding the standard deviation of a sample of the population. So keep that in mind. I mentioned it before. Alright, example 2. Find the standard deviation of the data from example 1 using the first formula. Alright, so to figure this out, because we have a very complicated formula, we're going to work out the formula in steps. But the formula that we're going to use, remember, is the sum. It looked not quite that nice. Sum of your xi's minus mu squared divided by n. So what we're going to look for first is we're going to find the xi minus mu, and then we'll take that value and square it. So let's make a chart so we have our data nicely outlined. So we'll have our xi values, which is our score. Then we'll have mu, our population mean, which we'll find. Then, taking apart our formula here, we'll find the xi minus mu first, and then we'll take that value and square it. Alright, I'm going to go ahead and pause the video and fill out the half of the chart at the moment. Okay, so I filled out the chart with the score values over here on the left. Now, to find the mean, remember to find the mean, you add up these values, and then we're going to divide by the number of values we have. So the number of values we have are 1, 2, 3, 4, 5, 6, 7. So mu is going to equal all the top values divided by 7, so I'll go ahead and add those up. So when I add them up, I get 562 divided by 7 is, we'll go ahead and approximate at 80.3. So that's the mean for the whole thing. And then for the xi minus mu, that'll be 85 minus 80.3. So go ahead, fill out the chart. I'll pause this video and fill it out myself. Okay, and then we'll go ahead and do these subtractions. So 85 minus 80.3 gives us 4.7. 77 minus 80.3, 3.3. I'll go ahead, pause this, fill this out, check back in with me in a second. Okay, so I've filled out those parts from the subtraction, and the last step we do is we take the values that we subtracted and we square it. So that'll be 4.7 squared. Let me move that over a sec. 4.7 squared. Then we'll do the negative 3.3, square that. 9.7 squared. I'll go ahead and pause the video and fill the rest of this in. Alright, once you've written them all down, we'll go ahead and do the squarings. So 4.7 squared, what is that? 4.7 times 4.7? 22.09. Then the 3.3, 10.89. Then the 9.7, 94.09. I'll go ahead and fill this out again. Okay, I've done all of the squarings. And now for the formula, what we need to figure out is what the sum of all these are. Because I need to fill that out right there. So on the side, I'm going to go ahead and write sum of xi minus mu squared is going to equal, I'll go ahead and add these up. When I add them up, I get 646.33. Alright, so, and when you have scratch work, and you can do this on your exam, for scratch work, go ahead, box it off on the side so I don't think it's part of your actual work, and just write scratch work. This keeps your work neat, and I won't end up grading this, okay? I'll grade what's not in the scratch work section. Okay, so, for the standard deviation by the formula, standard deviation is going to equal the square root of the sum, which was 646.33, divided by n. N is our sample size. So population size. 1, 2, 3, 4, 5, 6, 7. Okay, let's go ahead and compute this. So I plugged it into my calculator and took the square root, and I got it's approximately 9.6. And I'll go ahead and pause there, rounding off to the 10th place, unless otherwise directed. So, standard deviation is, using approximation symbols, 9.6. Now, we're going to go ahead and find the standard deviation using the second formula. So what was the second formula? Well, the second formula is standard deviation, the sum of the xi values, minus the sum of the xy's squared, divided by n, all over capital N, and then square root that. So, the items I want to find now in my column, I want to find the xi squareds, and then take the sum, and then what the xi values are. So let's go ahead and fill out our chart again. I'll write it down and then start the video again. Alright, so just copying down these values here, those are my xi's, and to fill that out, I want my xi's squared. So that'll be 85 squared, which is, let's see, I'm going to go ahead and fill out my chart. Alright, 85 squared is, whoa, bigger than that. I need more space. $85 squared is 7225. Then we're going to do 77 squared, then 90 squared, 62 squared, 83 squared, 74 squared, and 91 squared. I'll go ahead and pause the video and go ahead and work this out by yourself as well. Check back in with me in a sec. Alright, I went ahead and found all the squared values. Now what we want to find, for the formula, I need the sum of the xi values squared. And then, so the sum of the xi values squared, that's going to be from here, the sum of all those values. Adding all of them up, let's check what I get. Alright, when I add those up, I get 45,744. Okay, that is for this one right here in the green. Next, I want to go ahead and find this one. So I'm going to take the sum of those values and then square it. So first, let's find the sum of the xi. And then we'll take that and square it. Alright, and I get 562. So then 562 squared, whoops, is going to be, 562 times 562. Large number. That would be nice to see on a check, huh? Okay. Now let's go ahead and plug that into our work. So I'm going to go ahead and box this off sort of as my side work. And for the formula, finally, let's use this formula. So sigma equals the square root of the green value we had was 45744 divided by, and what was our red value? This was our red value here, the item squared. So minus the 315844 divided by n, and what is n? That is my sample size, or my population. 1, 2, 3, 4, 5, 6, 7. And all over, once again, divided by 7. Which I'll mark in the blue for 7. Okay, so just to make sure you know where every number came from. Okay. And let's compute this out. Simplifying the numerator, I'll end up with 436. 4364 divided by 7. And simplifying further, I'll get square root of 4364 divided by 49, which, when I take the square root of that, comes out to be approximately 9.43, which we'll go ahead and take to the 10th place, 9.4. Okay, so those are the two different formulas, the two different ways to get it. As you can see, because we did rounding, they are a teeny bit off, but once again, it will just depend on how you round. Alright, now let's take a look at the sample standard deviation, which is going to be denoted by lowercase s. And we are given the two following equivalent formulas, just like we had for finding the standard deviation of the population. We have the conceptual formula, which is s equal to, very similar to the one previously, you're taking your differences between the mean and the observations, adding them up, and dividing by your observations minus 1. So once again, please note, this is your mean, sample mean, and the x sub i's are your observations. This all simplifies out to square root of the sum of your observations minus your mean squared all over n minus 1. Now, the computational formula looks similar to the other computational formula. S equals the square root of sum of your xi values squared minus your sum of your xi values, and then squaring that. Once again, these two are different. Divided by your observations over observations minus 1. So what are the main differences between sample and population? It's that little minus 1. So we're going to go ahead and use the first equation to compute the sample standard deviation. of the sample obtained from the following formula. Alright, so first equation is sum xi minus x bar squared all over n minus 1. So all we need to do is first find the xi minus x bar, then square that. Let's go ahead and set up our chart. We have our xi's, we need to find our mean. After that, find the xi's minus our mean, and lastly, find the squaring of each of those values. So here are my data points: 85, 90, 62, and 83. So finding the mean of all these, let's add them up and divide by, and there are 4 observations. Alright, so our mean on the side is going to be 320 divided by 4, which is 80. Ooh, a nice number this time. And let's do computation. Xi, 85 minus 80, will be 5. 85 minus, 90 minus 80, 10. 62 minus 80, and then 83 minus 80. It's going to be 3, and that's going to be 18. Alright, lastly, let's take those values and square them. 5 squared, 10 squared, 18 squared, 3 squared. That's 25, that's 100, that one I'm not certain, and that one is 9. So let's go ahead and calculate 18 times 18. 324. Whoa, is that serious? Yes, sirree. Okay. So what we want is the sum of all those values. Alright, so scratch work on the side. So sum of xi minus x bar squared. Let's add all those up. Get 458. Alright, so plugging into our formula, standard deviation, sample standard deviation, is going to be the square root of my sum value, which I found out here was 458, divided by my n minus 1. N is the number of observations I see, which is 1, 2, 3, 4. So 4 minus 1. That'll be the square root of 458 divided by 3, which, what would that be? Okay, so that's approximately 12.355835, so on, which will approximate out to the 10th unless otherwise indicated. And there we go. So I'll write that out here. S, approximately 12.4. And boxing off my scratch work, which you would do on an exam. Scratch work. You could use SW to indicate scratch work. Alright, so now let's use the second data to compute the same thing. So what does the use the second equation to compute the same thing. So the second equation, which should give us pretty much the same result, sum of the xi squareds minus the sum of the xi, square that, divided by n all over n minus 1. Well, we already know what n is. N is 4, because we have 4 data items. Now we just need to find xi and the xi squareds. So the nice thing about this formula is it cancels out the need to find the mean. Notice in the other one we had to find the mean. In this formula, we don't need to find the mean. Let's go ahead and set up our formula box. It really doesn't require that much. I don't know why I made the box that big. $85, 90, 62, 83. Okay, so 85 squared, 90 squared, 62 squared, and 83 squared. What will we get here? I'm actually going to widen my chart a little bit because these values are a little bigger. All right. So 85 times 85 is 7225. Then 90 times 90 is 8100. 62 times 62, 3844. 83 times 83, 6889. Let me just check that one more time. Yep, all right. So let's see. The sum of the xi squareds is going to be these values. Let's add those up. And we get 26058. Then we want the sum of our xi values squared, which are going to be these values, added up and then squaring the product. All right, when I add them up, I get 320. Then we'll square that to get 102400. Okay, we have all the items we need now to fill out the formula for my sample standard deviation. So that's going to be the square root of sum of xi squared, which is this value right here, 26058, minus my sum value squared, which is going to be 102,400, divided by n, which is 4, because remember we have 4 items, 4 observations, all divided by 4 minus 1. Okay, let's see how we can simplify this. That'll be 3. And then simplifying that, what do we get? All right, we get 458, 458. Then plugging that in, what do we get approximately? So that comes out to approximately 12.355835, hey, which is what we had before, which rounds out to 12.4. So this time they actually rounded out a lot closer, the two different formulas, right there and right there. So that was nice. All right, so that's the way to use the two different formulas for finding the standard deviation. Now let's take a look at determining the variance of the variable from raw data. Oh, by definition, the variance of the variable is the square of the standard deviation. The population variance is denoted with sigma squared, and the sample variance is denoted with s squared. So that's pretty nice. If you want to find the variance, just square the deviation. Or if you want to find the deviation from the variance, you just take the square root. All right, example 6. Use the results from examples 3 and 5 to determine the population variance and the sample variance of the student's test scores. So example 3, what did we get from example 3? We got standard deviation of 9.4. So from example 3, we got standard deviation of 9.4. And from example 5, we got sample standard deviation of 12.4. Now we want to find the variance. So the variance is to just take these values and square them. So sigma squared is going to be 9.4 squared. And then s squared is going to be 12.4 squared. So when we calculate these out, let's see. 9.4 times 9.4 is 88.36. And 12.4 times 12.4 is 153.76. All right, so there we have the variance and the standard deviation, the variance for both the population that we are looking at, and then the variance for the sample of the population that we were looking at. So just squaring them. Now let's take a look at the empirical rule, and we're going to use it to describe data that are bell-shaped. All right, remember bell-shaped is when you have data that looks something like that. The empirical rule, it's often also known as the 68, 95, 99.7 rule. What on earth does that mean? Well, these are 3 important values that we use when we're looking at the empirical rule. So if a distribution is roughly bell-shaped, then the following holds. let me draw a better bell than that. So, approximately 68% of the data will lie between one standard deviation. That is, approximately 68% of the data lies between mu minus 1 times your standard deviation, where remember mu is the mean, and mu 1 plus the standard deviation, which would be in between one standard deviation away from your mean. So that would be about 68%. I'm going to go ahead and draw this on the bottom here. You might not have room for it, but just a visual for you. So this is for 68%. Oops, that's the mean. We have our mean minus 1 sigma, mean plus 1 sigma. And that gives me the 68% right there. So the next one we have is the 95%. So what do we know for this one? Well, this one is 95% of the data will lie between two standard deviations of the mean. That is, approximately 95% of the data will lie between mu minus 2 sigma and mu plus 2 times sigma. So here'd be mu. This would be one standard deviation away, but we're looking at 2. 1 minus 2 sigma. 1 plus, oops, sorry, not 1. Mu plus 2 sigma. Okay, so the red lines would be where the 68 was, but we're looking at the green lines, which would be 95% of the data. Oops, and this was 68%. And lastly, another one of the important markers that comes from the empirical rule is when we're looking at 99.7% of the data will lie between 3 standard deviations of the mean. That is, approximately 99.7% of the data will lie between mu minus 3 sigma and mu plus 3 times sigma. So let's take a look at this. That's 1 standard deviation away. Now notice these are very approximate tick marks I'm doing. 2 standards away, and 3. We're looking at the 3 standards away. So that I'll do in green. This was the 68 in red. Remember, it's very approximate. The 95 in blue, but we're looking at the green area, which is all of this, so it's bigger. 99.7% of the data will lie in between there. Okay. So note, we can also use the empirical rule based on sample data with x bar, so the mean, used in place of mu, and with s used in place of standard deviation. Okay, so you can do this with both population values and sample values. So let's take a look at this example. The following data represents the weight in grams of a random sample of 50 candies. The standard deviation is given already as 0.7 grams. Use the empirical rule to determine the percentage of candies with weights between 0.7 and 0.98 grams. Hint: we have a sample mean of 0.84. Alright, so whenever anything talks about using the empirical rule, it's always a good idea to go ahead and to draw out the graph of the bell curve and to label all the values you would need for the empirical rule, which would be your 68, 95, 99.7 marks. So our mean is 0.84, which means 1 standard deviation away from that would be my 68. So let's go ahead and calculate that. So 1 standard deviation away would be, so normally it's mu minus 1 sigma, but remember we're using, these are for population, we're using sample. So instead of mu, we're going to use x bar minus 1 times the standard deviation, which is s. So that'll be 0.84 minus 1 times 0.07. So let's go ahead and calculate that out. So we have 0.84 minus 0.07, which is 0.77. All right, we can mark that down, 0.77. Then, to find, so this is all scratch work I'll be erasing. To find the other side, for the one standard deviation away, you do plus 0.07. Calculating that out, we get 0.84 plus 0.07, which is 0.91. Alright, so that was the first standard deviation away. Go ahead, I'm going to pause the video and write down the other standard deviations. Do the same. Alright, so I've gone ahead and identified the 68%, so one standard deviation away, then the 2%, or sorry, the 95%, which is two standard deviations away, and finally the 99.7%, which is 3 standard deviations away. So we want to find the percentage of candies with weights between 0.7 and 0.98. Do I see those values on my graph? In fact, I do, right here, 0.7 and 0.98. And we know the percent inside the standard deviation away is 95. So that would be my answer. So the percentage of candies between 0.7 and 0.98 grams is 95%. Box the answer. So now we're asked to determine the actual percentage of candies that weigh between 0.7 and 0.98 grams. And how do we do that? We'll determine the actual one. We're going to go ahead and count out the actual values here. And we know that there are a total of 50 candies. So the actual percentage is going to be however many that are between 0.7 and 0.98 and divide that by 50. Okay, I'm going to go ahead and count those out. Let's see. Alright, so I marked this up with the values that are between 0.7 and 0.98 inclusive, and the only one that is not is the 0.99, which means that 49 out of the 50 are between 0.7 and 0.98. So calculating this out, what do we get? About 98%. Okay, so when we use the empirical rule, we were close, but we were not perfectly close. Okay, so this would be the actual percentage of candies when you actually count out each of the values. So now we're going to go ahead and use the empirical rule to determine the percentage of candies with weights more than 0.91 grams. So let's go ahead and refer back to our graph over here. I'm going to copy it down for a second. I'm looking for the value 0.91 when I'm using my empirical rule deviations. And I see it's right here, which is in red, which is my one standard deviation away. Let's go ahead and copy that down. Oops. So I want to find out the percentage that is greater than 0.91. Well, how do I do that? Let's use some geometry tricks here. I know that this area here is 68%. And I know the whole area under the entire curve is going to be 100%. So the whole thing, 100%. Which means that the blue area left over here is going to be 100 minus 68%. Whatever that's going to be. Actually, let me use a different color than blue since that's already for the whole item. Let's use this to represent. So finding this value will be 100 minus the 68. So how much is that? 100 minus 68, that's going to be 32. So these two total areas here, when I add up their area, would be 32%. But I want to find out the area greater than 0.91. And the area greater than that is going to be here. It's only going to be half of what I'm looking for. Well, to find that out, I'll just take half of the 32. So half of 32, and what's that? 16. So this area here is 16%. Okay, so what percentage of candies weigh more than 0.91 grams? 16%. So, let's see how would I write that out. 16% of candies weigh more than 0.1 grams. Okay, so it was using a bit of the empirical rule and then also just some concepts using sort of like geometry figures. Now we want to determine the actual percentage. So when you want to determine the actual percentage, you're going to go back up and count. So we want the ones that weigh more than 0.91 grams. Let's look at our chart here. Which ones weigh more than 0.91? So we have this one, that one, that one, that. Alrighty. Let's count those up. How many are they? 1, 2, 3, 4, 5, 6, 7, 8. So 8 out of 50. And what's that? 16. 0.16, which would be 16%. Alright, so the actual percentage is 16. So this time, it is actually quite accurate when I calculated. Okay, let's take a look at the last objective for this. This is Chebyshevs, which I think is how to say it, inequality to describe any set of data. So for any data set or distribution, at least 1 minus 1 over k squared times 100% of the observations lie within k standard deviations of the mean, where k is any number greater than 1. That is, at least 1 minus 1 over k squared times 100% of the data lie between mu minus k sigma and mu plus k sigma for k greater than 1. So it's similar to the empirical rule, but it's not quite as specific as the three values that we had, the 90 or the 68, 95, 99.7. Alright, note, we can also use Chebyshevs inequality based on sample data, which is good to know, so it doesn't have to just be the population. And also note that Chebyshevs inequality applies to all distributions regardless of shape. But the empirical rule holds only for distributions that are bell-shaped. Okay, keep that in mind. Alright, so we have a problem here. So, in December 2018, the average price of regular unleaded gasoline, excluding taxes in the United States, was $3.06 per gallon. Assume that the standard deviation price per gallon is 0.11 cents per gallon, and use Chebyshevs inequality to answer the following. What minimum percentage of gasoline stations had prices within 4 standard deviations of the mean? Okay, so one thing to notice here is it says minimum percentage, and in our Chebyshevs inequality, it talks about at least, so that's good. And we want to have 4 standard deviations. So in this case, k is going to be 4. So we'll just go ahead and plug that in. So k equals 4. Plugging that into our equation, we have 1 minus 1 over 4 squared times 100%. Okay, so calculating this out, let's see, 1 minus 1 over 16 times 100%, and we'll get 0.9375, timesing that by 100%, which we end up getting, or we can end up rounding to 93.75, so that'll be 93.8% if we round to the tenths place, depending on how they tell you to round. So 93.8% at a price within 4 standard deviations. Now let's take a look at the next one. So what minimum, okay, once again we're using minimum, which is good, had prices within 2.5 standard deviations of the mean. Okay, so this time k is 2.5. Still using the same formula though. We have 1 minus 1 over 2.5 squared times 100%, which will equal 1 minus 1 over, okay, so 6.25 times 100%. Plugging that into the calculator, it would then come out with 0.84 times the 100%, which is going to be 84%. Now it's asking for what the gasoline prices are that are within 2.5 standard deviations of the mean. So now we need to look at the actual prices. So to do this, we need to figure out what the mean and the standard deviation of our gasoline prices are. So the mean, looking up at the beginning here, average price of the mean, so 0.36, and then the standard deviation was 0.11 cents. So let's write this down. So the standard deviation was 0.11, and the mean is 3.06. And then calculating these out like we've done with the empirical rule, to find within two standard deviations, you're going to do the mean plus 2.5 times your standard deviation, and, sorry, my cat was making weird meowing noises, so I have now removed my cat from my room. I will continue. The next one would be your mean minus 2.5 times your standard deviation. So plugging those values in, we have 3.06 plus 2.5 times 0.11, and 3.06 minus 2.5 times 0.11. We can calculate those out. Okay, working that out on a calculator, you can get 279, and, oops, sorry, that's the wrong one. You get 334 and 279. So what are the gasoline prices? The prices are $3, so remember your units when you're writing out a sentence, and $2.79 within 2.5 standard deviations. All right, let's take a look at the last problem. What is the minimum percentage, once again looking at the key term minimum, of gasoline stations that has prices between $2.75 and $3.39? So this is kind of the reverse of the problem we just did. Last time we were given the standard deviations, and then this time we're given the values. So it's a little bit reversed, not quite. But so what we want to do is first find out what the standard deviation is we'd be looking at, or how many standard deviations away we'd be looking at. So to do that, we're going to go ahead and let's use K. K, because that's what we're trying to find. We're trying to find K because when we plug K into our formula, we can find out the percentage. Okay, so the formula we have, we're trying to find K, remember? Well, we know that mu minus your standard deviation, which is going to be K in our case, because we don't know what the standard deviation is, times sigma, or we could use the version mu plus K times sigma. We could use either one, because we're given both intervals. But I'll go ahead and just use the 0.39. That's going to come from the addition version. And what do I get? Well, I know my mean was already 3.06. I was given that earlier. Plus K, which we're trying to find. And then my sigma, or my standard deviation, was given earlier, which was 0.11. Okay. So, backtracking on this. We know that this equals 3.39. Now we need to solve for K. Let me box this off. Okay, so to solve for K, we'll go ahead and minus 3.06 from both sides. Then we get K times 0.11 equals 0.33. Dividing both sides by 0.11. We have that K equals 3. So awesome, now we have found K. And once again, you could have done it using the other version, which you would have set equal to the 2.75 and filled in your mu and your sigma values. You could have done that. We find out that K equals 3. So now to find the percentage, we're going to use our formula here for the percentage, which should have a percent. So to find percent, we'll plug it in 1 minus 1 over, and my K value is 3, times 100%. That's going to equal 1 minus 1 over 9 times 100%, which will come out to be, and that comes out to be a long set of repeating decimal of 0.8, which we can round out to 0.889 times 100%. And once again, this would depend on what you were given in terms of rounding. I think oftentimes in Pearson, you're told to round to 2 decimal places. So if this was with Pearson, actually, we would do that, and then we get the 88.89%. So rounding out to the 2 decimal places, 1, 2. All right, so there we go. That's the percent. So that is the minimum percentage of gasoline that had prices between 2.73 and 3.39. All right.